Yeah. Hi, everyone. My name is Newton, and this is Anton. And we'll be talking about parallelizable decision trees to efficiently minimize reliance on missing values. To start, let me set the context of the project. So missing values are common in many applications of machine learning. And this often complicates deployment of these models in prediction tasks. In many safety critical domains, we want decision-making functions or models that are interpretable, which motivates our use of decision trees. And imputation of values can often bring problems downstream, especially if you're looking into scenarios where the missingness is not random, where there is maybe some relations between the missingness. For example, you can think of a situation where when a patient goes to a hospital, if they don't have a cognitive score, they probably won't have an MRI taken. So there is some pattern in the way in which missingness occurs. And in this work, we want to learn decision trees that avoid relying on missing values. And how do we do that? So we feed decision trees so that missing values rarely occur in the decision paths. So when you train decision trees, typically you have to impute the data before you train. But we will want trees that avoid paths where the features were originally missing in the decision rule. And the basic idea is that we regularize the node splitting criteria to account for the presence of missing values. So typically how you build a decision tree is you work with some sort of score like a Gini score or entropy. And then we also add a regularization parameter or term to the objective. Here we just have like a summation of if the values were missing or not, and we multiply it with a hyperparameter alpha. And this sigma I is to account for the case where you also want to train like a random forest. You could also tune this in some way. And this helps us build trees with a low missingness reliance. So missingness reliance is a metric that we use, which basically counts how many of the missing features or in the decision paths. So here it's marks, but you can also use a summation of the number of features that pass along the decision path, which is what we do in our implementations. Yeah.
Yeah, so we have implemented this already, and we see that we can learn. So here I showed you missingness reliance in that plot, and here it's your AUC. So the blue boxes are the missing most avoiding decision tree, and you can see that we can minimize reliance on missing values while keeping maintaining performance. So we also include a lasso model here. That's not part of the WASP project, but you can also build other types of models that avoid relying on missing values. So it seems to work, but our current implementation is based on line Python code, and it's not very scalable. So we would also like to extend this idea beyond just decision trees. So you can also think of like mixedness avoiding random forest models or grading boosting models that avoid relying on that. And yeah, as you understand, if you have many trees or you gradient boosting tool, you would require, you would need an efficient implementation. So that's where the course is handy. Right. Okay, so in this project we compared 3 different types of implementations. So the first one is the one that we already had, the Python-based implementation, but we also did an implementation in Scala. So it will be exactly number 2 here, where we basically there is this implementation in Scala which we modified to handle this missingness avoiding feature, and also we also played around with just using replacing like parts of the Python code with PySpark operations to see if that could also work, and that would be a more simple approach. And here we compare some running times for these 3 approaches. But yeah, so the naive implementation in Python is we just recursively build a tree, and for each node we iterate over all the features and all the split thresholds to find the best split. And of course that works okay for small or medium-sized data sets, but as I said before, if we want to do this in a larger scale, it's just too slow. So to implement this in Scala, we forked the Spark repo and created a new branch and made trees where we implemented these missingness avoiding decision trees without disrupting existing code. We are new to Scala and we are new to Spark, so it was quite difficult. So it felt like it was simple, but it was it took a lot of time to just get it to work. It's a massive code base, and it's like it's very nested. So like we wanted to change like parts of the code that was related to the decision trees, but trees are also foundation in random forest and gradient boosting as well. So it was a bit tricky to get it to work. And also building Spark from scratch takes like 45 minutes at least. So that slowed down our iteration process. But we basically did this, and we updated the existing decision tree classifier to avoid relying on missing values. So you pass a missing MS mask to your model and this regularization parameter alpha. And then we get all the features that are already implemented in Spark. So Spark, the decision tree implementation in Spark is highly efficient. So splitting statistics for each node feature and split are computed in parallel. We can distribute that. And then also Workers operates on repetition of the data. So having a large data set is not a problem. You can check it up. And then the actual node splitting is performed by a single worker, which gets aggregate statistics. So it's nice. We can use this, and we had this missingness avoiding feature. So you know. So basically, what you need to do now is just to so this is the Scala. You have the decision tree classifier. You need to set the features and the label. But now you also set a missingness column, and you set the alpha parameter, or you use the PySpark wrapper, and you can do the same thing there. And so it's available. We can clone the repo, check out our branch, and then you build Scala from scratch, and you have our features. Right.
Yeah. Right. So while fighting with the Scala code base, we also thought it was a good idea to try like a PySpark Python implementation, which doesn't enjoy the same benefits of the optimized Scala decision tree and needs some improvement. yeah, so we basically tried to apply some of the Spark code transformations and actions in computing the missingness or aggregating the scores and these kind of things. Yeah, and some of the tools we used include, we had two cluster implementations. So one was on Tetralith and one was on Alvis. And for the PySpark implementation, we also had like a locally containerized Docker setup. This is our code setup. So we have the PySpark matrees here, and we have some other functions to work with the cluster Spark. So for the local setup, we had a Docker server with 2 workers, and we also wrote scripts to automate submitting of jobs, which basically is starting the Docker server. You copy your files to the Docker context, and you submit jobs to the Docker container with Spark Submit. And for the cluster setup, we built the Spark code that we had changed and run it with the local star setup, which basically means that you use all the available cores as workers. Right, and we have some results for the running times. So the thing to look at is the blue line here. So this is the Scala Spark implementation. You can see that it's kind of constant compared to the decision tree, which kind of grows linearly. And also the PySpark needs some improvement, as I said. We're still doing some iterations in computing the splits, but we are going to improve that. And we also have some running times here reflecting the same thing. Yeah. And this is an example of a tree that comes out with some simplistic data.
Okay, some to-dos. So I think so yeah, as Anton said, when we run this on the cluster, we just used thing in node with a local master with all the cores basically. So it would be nice to set it up in a more distributed way on the cluster, and also experiment with partitioning on the data. So we had some memory issues when we try to load all the data on one node basically. So distribute that with it. Yeah, I guess this was just for example that we showed here. We had synthetic data, but of course for a reboard or like for a realistic data set, we need to use hypermeter tuning. Yeah, as Anton indicated, there might be some issues with PySpark implementations, so we should do it on that. And then add a function to compute missingness reliance in these Scala-based trees. So right now we are not really able to find out the extent that we rely on missing values in those trees. And we also, the current implementation is only for numerical features. We need to modify the code a bit to make it work for categorical features as well. And then the next step would be to integrate this also for forest and gradient boosting in Scala, which shouldn't be too difficult. It's just a wrapper around the decision tree model. Okay, I think that was it for us. Yeah, it's part of our research project. So yeah, I think for that project we can use the plain Python implementation, but yeah,
we saw a bit of opportunity in the course to play around with a more efficient implementation. But yeah, the idea is to we are writing a paper on this to maybe consider like from linear models to decision trees and grading boosts.
Just curious, like assuming you didn't have experience with ScaDaMaLe, as you said, like how many hours roughly?
Oh my god.
Yeah, it might seem that this is a very simple to implement, but yeah, without any experience in Scala, it was we spent a lot of time just setting it up because it like what according to the Spark developer guide, you should be able to set up in IntelliJ and like work like you normally would do when you at least when I program to debug efficiently and so on, but we didn't manage to set it up, so we ended up just make a change and you build the entire rep from scratch more or less, so we take like 45 minutes. I think there must be a more efficient way of doing it, but we went in that direction. So, yeah, it was.
Yeah, and to also find the interdependencies within the classes is kind of hard. So you make a change in one place and everything breaks down. Just
how you read what so the gradient is the random forest, all of these things, except it can be very highly used settings, like this insurance, so many sectors that could be really good.
In terms of performance, is your conclusion that Spark is faster than Python?
Yeah, it is. I mean, if you look at this graph, you can see that the Python implementation sort of increases linearly, and this is kind of so it's much better.
Yeah, I mean it's super efficient. And also they do a lot of like optimization, like they do binding up the features and so on to you don't have to iterate over all features and yeah, everything is distributed across workers. So I don't know how it compares to like sklearn imputation efficient tree. That's quite efficient also, but maybe not as scalable for large data.
Okay, if there are no questions.
Right, Sofika should be here. Maybe someone can check outside. I don't know.